So we are continuing the Fermat's theorem, where it says that if f or the function has a local maximum or minimum at c, and if f or the first derivative of the function at that point c exists, then that function, the first derivative of the function at the point should be equal to 0. So we are going to unpack this. So if you haven't watched the previous video, I shall drop a link in the description for you to access that. You can go back to watch so that you can go through this proof. Then let's move through this proof. First, let's suppose that f of the function has a local maximum. And if the function has a local maximum, that means that the function at that c should definitely be greater than or equal to the function at x, where we know that the x lies within the domain of the restricted interval or of the interval, where this function at c is the local maximum. Then we know that that also implies that if there's an h which is sufficiently close to 0, where h is definitely either positive or negative, where we indicate that h should be greater than 0 or h should be less than 0, then we can reput this as my function at that c should still be greater than or equal to my function at my c plus h. Okay, with this, let's put that well. Now let's arrange that. Okay, plus h. Okay, with this, let's rearrange this. We are going to have a function at c plus h minus the function at c will definitely be less than or equal to 0. So as we have this, let's consider h being greater than 0, which means that we are taking this part where my h is greater than 0. Then let's divide through by my h. Dividing through by h, I'm having the function at c plus h minus the function at c, which is less than or equal to 0, all divided by h. This as well divided by h. Then what does that mean? This is giving us the function c plus h minus f of c all over h should be less than or equal to 0. Then we can also take the right hand limit. Since this is greater than 0, let's just consider taking the right hand limit of both sides. That is going to mean that I'm having my limit as my h approaching 0 from the right hand side of my f at c plus h, okay, minus the function at c all over h should be less than or equal to limit as my h approaching 0 from the right hand side of 0, which this is definitely equal to 0. Okay, so with this we can now put that my limit as my h approaching 0 from the right hand side of f at c plus h minus f at c all over h should be less than or equal to 0. But since we know that the derivative of the function at c exists, then we can say that since the f prime of the function at c exists, which is the same as the limit as h approaching 0 of the function f of c plus h minus the f of c all over h is going to be equal to this everything that is here, which is limit as my h approaching 0 from the right hand side of the function c plus h minus f at c all over h, which is definitely less than or equal to 0. And what does this mean? This is telling me that my first derivative of the function at c is less than or equal to 0. So we have now proved or seen that the first derivative of the function at c is less than or equal to 0. Now let's reconsider the fact that h is less than 0. For what we took earlier, we realized that we took when h is greater than 0. So let's take the other part where h is less than 0. So here my h is less than 0. But where did we substitute that? It means that when we come here, we are going to divide through by negative h over here. where we are having that f at c plus h minus f at c all over my h should be greater than or equal to my 0 divided by h. Why this? Because when we divide through by the negative h, when we divide through by negative h, the inequality changes. Since the inequality changes, we now have this result. This is telling me that I'm finally going to take the left hand limit of this. Taking the left hand limit, I'm going to result in f, so this is going to be limit as my h approaching 0 from the left hand side of a function c plus h minus the function at c all over my h should be greater than or equal to 0. What does this mean? So let's divide this first. Alright, so since my f prime of the function at c exists, which is the same as my limit as h approaching 0 of the function at c plus h minus the function at c all over h. Since this exists, then it should be equal to this guy, which is the same as my limit as my h approaching 0 from the left hand side of the function at c. So let's take that well. Function at c plus h minus the function at c all divided by h, which is greater than or equal to 0. What have we just proven? We have just proven that the existence of the first derivative of the function at this c is less than or equal to 0. Then we can see that we have derived that a function at the first derivative of the function at c is greater than or equal to 0. But from the previous one, we have also seen that a function f prime of the function at c is also less than or equal to 0. Now, we have now gotten these two, which the first one is this and the second one is this. So let's put all of them together. We are first having that the first prime of the function at c is less than or equal to 0, and the same time the first prime of the function at c is also greater than or equal to 0. And since both of these two conditions must be true, then the only possibility that we can take over here is that the f prime of the function at c should be equal to 0. That is what the Fermat theorem is saying. It said that if f has a local maximum or minimum at c, and if f prime of the c exists, then the f prime of the function at c should be equal to 0. Alright, so we're now going to continue where we see the limitations, or we see what what we have to note about it. So let's note that when the first derivative of the function is equal to 0, f does not necessarily have a maximum or minimum at c. What is this saying? This is an if and then statement. This is saying that if f has a local maximum or minimum at c, and if f prime of the function at c exists, then the first derivative of the function at c is equal to 0. But it's saying that the converse is not true. It means that if the derivative of the function at that point is c, then that does not necessarily mean that the function has a local maximum or minimum. So he's just saying that the converse is not true. It's not always true, which is this. So let's analyze this graph very well. We realize that our function is giving us what? My y. So let's put that. My function f of x is equal to x to the power 3. So let's take the first derivative of the function, which is going to be what? 3x squared. This is f. This is f prime of x. Sorry, let's put that well. Alright, so this should be equal to my f prime of x. So when we have what? My f prime of 0, this should be equal to what? 3, 0 squared, which is the same as 0. Alright, since even the conclusion part, this is true, the first derivative of the function is 0, does not necessarily mean that the function has the function has a local minimum or maximum. So when we consider this graph, we can realize that yes, even though the derivative of the function gives us 0 at 0, this does not indicate that the function has a local maximum or a local minimum.